This lesson covers the topics of work and energy. First, let's review the definition of energy, and this is going way back in the year. Energy was defined as the ability to do work. Remember, we had potential energy, that was stored energy or energy that was at rest, and this came in the form of gravitational potential energy, chemical potential energy, elastic potential energy. And we had kinetic energy, that was energy in motion. We learned about mechanical energy, that is the energy of the moving parts of a system. Electrical energy, when electrons are flowing through a circuit, that's a type of kinetic energy. So these are all different types of energy, and energy is defined as the ability to do work. But in science, we need to understand more clearly what exactly do we mean by work. In science, work has a very precise meaning. It happens only when a force makes something move through a distance. If nothing moves, then no work is done. So for example, if you push on a really heavy boulder, you might grunt and strain and sweat no matter how hard you push on that boulder. If it doesn't move, you haven't done any scientific work on it. So again, work only happens when a force makes something move a distance. The formula for work is simply the force that's applied times the distance the thing moves. Force is measured in newtons, and distance is measured in meters. So the units for work should be Newton meters, newtons times meters. They are in fact Newton meters, and we compound this into a unit called a joule. Joules are the units for both work and energy. Since energy is just the ability to do work, it makes sense that both of them would be measured in the same units. So a joule is the amount of work done when you use a force of 1 Newton to move an object a distance of 1 meter.
This woman is working in her garden. This man also appears to be working. We might think that the man who is struggling to move the rock is working harder than the woman who is using a trowel or small garden shovel to dig up the soil. However, to a scientist, only the woman is actually doing work. The man may be straining and his muscles might ache, but because the rock isn't moved, he is doing no work. The woman, however, is accomplishing work because she is lifting and moving the soil from one place to another. Scientists define work very specifically, and to them, work is accomplished only when a force is used to move an object a distance. Scientists have a formula that is used to calculate the amount of work accomplished. Work equals force times the distance moved. In the English system of measurement, the force is measured in pounds and the distance in feet. So, if a person picks up a garbage can with 15 pounds of garbage and moves it 3 feet off the ground, the amount of work is 45 foot-pounds. In the English system, work is measured in foot-pounds. In the metric system, the Newton is used to measure force, and the meter is used to measure distance. If someone lifts a suitcase with a force of 50 newtons 1 meter off the ground, they have done 50 Newton meters of work. A Newton meter, or joule, is the unit of measurement used in the metric system to represent work or energy. 1 joule is equal to something weighing 1 Newton lifted 1 meter. Let's calculate the amount of work being done by this man as he works with this exercise equipment. Each bar weighs 10 pounds. He is lifting 20 pounds 2 feet. The formula is work equals force times distance. So the work the exerciser has accomplished is 40 foot-pounds.
So what does all of this have to do with your mousetrap car? Well, the amount of potential energy that's stored in your mousetrap car, it's the same for every car, because every car has just one mousetrap. And the springs in those mousetraps are essentially identical. So all of the cars in the class start out with the same ability to do work. They have the same amount of energy. The setup of your car, how big your wheels are, where the axles are, how much friction there is, how long your lever arm is, determines how much of that work ends up as force pushing the car forward. We need to understand the concept of mechanical advantage a little bit to understand why things like the lever arm size and the wheel size matter in our cars. Here's an example where you would use a pry bar, that's a long bar balanced on a fulcrum or a pivot point, to lift a heavy rock. So you know that if you're trying to lift something heavy, one good thing to do is to stick a stick under the heavy object and then use leverage to lift that object up. So if you look at the two sides of this lever, the work being done on both sides is the same. But notice that on the left-hand side, because the left-hand side of the bar is moving through a distance of 5 feet, the effort that's required is lower. I don't have to push with as much force because I'm moving the left-hand side of the bar through a greater distance. On the right-hand side of the bar, the force that I have to overcome there is 100 pounds. That's the force of gravity pulling on that load. But the load only moves through a distance of 1 foot. So notice that on both sides, the work done is 100 foot-pounds. But on the left-hand side, more of that work is done through a greater distance, and on the right-hand side, more of that work comes from a greater force. So in your mousetrap car, if you have a short lever arm, the distance that the lever arm is moving through is low, and so the force that's going to be applied to your axle to spin that axle is higher. If you have a really long lever arm, the distance that lever arm is going to move through is much higher, and so the force that's going to be applied to your axle is much lower. One thing you can adjust in your mousetrap car is where the string that spins your axle attaches to your lever arm. If it attaches closer to the mousetrap, that makes a shorter lever arm. If it attaches further away from the mousetrap, that makes a longer lever arm. A quick review of force. Remember that force measures the push or pull of one object on another, and that force is equal to mass times acceleration. The units of force are the Newton. And a Newton was what we got when we multiplied a kilogram by a meter per second squared, the units of mass times the units of acceleration.